This video shows you the conversion of the EES Rankine cycle setup to an actual EES model. Here, to refresh your memories, are the givens. Steam enters the turbine at 600 pounds per square inch. That's in absolute terms. At 1,000 degrees Fahrenheit, it exits at a two-phase mixture temperature T, which we assign to be 80 degrees Fahrenheit. That obviously could be altered. Condensate exits the condenser at T minus 5F and is pumped to 600 pounds inches squared. And we assume that the turbine and pump efficiencies are 90 and 80% respectively. The net power output is 1 megawatt. So we're looking for quality at the turbine exit, the steam mass flow rate, and the thermal efficiency of the system. We can explore parametric studies, but that is the gist. So in EES, I'd like to label a comment for given, then list all the given values offered. So P1, T1, T1 absolute if I need that, T2, T3, T3 absolute, the efficiencies of the turbine, the pump, the inputs in SI, in terms of 1,000 kilowatts or 1 megawatt, and a conversion into BTUs per hour for English units. Finally, we note that P3 equals P2 and P4 equals P1. I like to usually input into the diagram window a state point diagram so I know exactly what I'm talking about here. P3 and P2, does that make sense? Yeah, there's no pressure drop through the condenser in this case, and that no pressure drop through the boiler. In an actual boiler and condenser, there will be pressure drops, but this is a relatively simplified Rankine cycle. Stepping down, first lookup we talked about in our notes was the H1 and S1 lookup, so that's here. We know the T1 and P1, so we can get it. That's because it's in a superheated region. S1, again, similar lookup, just a different function. Stepping around the cycle to 2, we can use the efficiency equation that we used in the setup. H2 can be found this way. H2S can be found assuming S equals S1, which we calculated above it. X2 is the quality, which is a function of T2 and H2. P2 we can calculate as a function of T2 and X2. Continuing around, working around in a clockwise fashion to T3, enthalpy of 3, we can say is a function of T3 and X equals 0. We're going to say it's fully condensed when it reaches this pump. H3 subcooled would be a enthalpy of steam in a T and P combination. Notice we switch from an X to a T and a P. S3 would assume that steam can be a function of T. We can look it up as a function of T and H. Enthalpy, H4S, so the isentropic enthalpy coming across the pump could be P1, that high level pressure, plus an S value that's equivalent to what comes in. In other words, we've gone up vertically on the TS diagram. Walking once again through energy now. So the gist, taking a moment to pause here, is to use your property lookups, use your efficiency equations, and also use your energy balance equations. In each stage, each component apply those methods, properties, efficiency, energy, sometimes mass too when the cycles get more complicated. Walking down to the next line, H4, using the efficiency of the pump equation, the work net, recognizing that the specific work would be the work output from the turbine minus the work input of the pump. So what this H4 minus H3 is. Once again, always in specific work terms. But we can calculate the m dot, the unknown steam flow rate, by taking the given work output and dividing through by the specific work output. Okay, the final setup is QB for the boiler, the eta thermal efficiency, the eta max. I added this just to see how we compare to Carnot. And then this was just going to be a look at the maximum work in the cycle in English units and SI units. There are some additional smart checks, but they're more advanced and certainly not asked for in this particular problem. They involve basically checks for entropy and overall energy balance. So let's check, see if we have the right number of equations and variables. We do. We can then solve for this problem. And in this case, we should be clear about what we were looking for and what we calculated. So let's bring up that other window that specified what we were looking for. Steam quality at turbine exit. What would that be? That would be the X2. Did we calculate that? X2, yeah, it's almost 90% quality. The mass flow rate, let's see, that should be an M dot term. Here it is, 6,400 roughly pounds per hour of steam, and a thermal efficiency of 0.36 compared to a Carnot of 0.63. In review, what you want to do is make sure that you take what is given on paper, take that which is given to you, and work out the equations for each component one by one. Move from paper to code. You want to clearly document everything that's given, and then walk systematically through each component one by one, entering equations for property, equations that take benefit of the efficiency definitions, and then finally take benefit of energy conservation equations. I hope this was useful, and it certainly unlocks some interesting abilities to do parametric studies. If you want to look at the impact of, let's say, the turbine efficiency, you would highlight this, add a comment. Notice that when I check my equations, there's one less equation available. I would then go into a parametric table and vary that thermal efficiency, in this case from 0.8 to 0.9. How do you do that? You say alter values, put in 0.8 to 0.9, click OK. You click the thermal efficiency, you hit go, and that would be the impact of turbine efficiency. If you want to see the impact of pump efficiency, you can repeat the same process. You'll find that there's very little impact on pump efficiency. And that's consistent with our fact that the pump in a Rankine cycle requires very little work compared to the outgoing work of steam expanding in the turbine. I hope this has been helpful. And, EES is certainly powerful, so I hope you enjoy using it. Thank you.